תודה רבה עופר, אנחנו נחזור לדגש הטכנולוגי, והדובר הבא הוא דן לב, דוקטור דן לב, קיבל את תעודת הדוקטורט שלו בשנת 2012 מאוניברסיטת פרינסטון, בה התמחה במנועים חשמליים לחלל. כיום הוא עובד בחברת רפאל, בה הוא חוקר ומפתח מערכות הנעה לחלל. כחלק מעבודתו הוא ביצע את שלב התכן הראשוני של מערכות ההנעה של ננו לווייני סמסון, השתתף בשלב הבדיקות וניתוח הביצועים בחלל של משימת ונוס, שימש כיועץ טכני בפרויקט לוויין התקשורת עמוס 6, הוא משמש כמוביל טכני בפרויקט הישראלי-אירופאי מפס ללווייני מיקרו. דוקטור דן לב.
Thank you very much. Perfect, you can hear me. So, very excited to be here. Thank you very much for having me here. Today I'll give you a presentation on 3 different propulsion systems, 3 different propulsion solutions for small satellites, everything made by Rafale. I'll do that by first tell you why small satellites are so important. Why are we targeting this specific market? Then we'll go over the solutions by Rafale, 3 different solutions, cold gas, chemical propulsion, and electric propulsion systems. So, in the past decades, there has been a major increase in the usage of, in the deployment of small satellites. And everyone has been talking about it in the past few hours. We see that tens or maybe a couple of dozens of launches about 10 years ago became hundreds of launches these days. And the forecast shows us that there's an increasing number of satellites being launched every year now. So, in essence, we can say that the number of small satellites is increasing every year. Now, we know that's not a big surprise for you, but what we can also see is that the role of these satellites is also increasing over time. It's changing, it's migrating. So, if about a decade ago, these satellites were mainly technological satellites, technology demonstrators, satellites that were there just to try new technologies, were living in space for about 1 year. These days, these satellites have to live longer. They're commercial in nature. They have to maneuver, so they have to change their orbit, maybe have some orbit corrections. Some of them are becoming bigger, so they have to deorbit when they change their lives, when they end their lives. So it boils down to the fact that there's an increasing need for some maneuverability, for some propulsion need on board these satellites. One more thing, these satellites are becoming bigger. If the baseline about 10 years ago was 1 U CubeSat, 10 by 10 by 10 centimeters, these days the baseline is closer to 6 U. And future satellites are becoming bigger, so they're going to be 12 U. More companies are talking about launching 18 and 20 and maybe even 24 U satellites, satellites that weigh tens of kilograms. Okay, so I hope I convinced you at this point that there are more satellites launched every year now. They're becoming bigger, heavier, and there is an increasing need in means of propulsion for these satellites. So ideally, the most suitable form of propulsion would be a propulsion system that's, first of all, affordable, which means that it's suited for the low-cost satellites that we see launched in past years. It is loosely coupled, plug-and-play type system, very simple interface. And it is very flexible in the sense of the mode of operations or the capabilities the system has. Either one system, which is flexible, or maybe multiple systems. Each system can be devoted or dedicated for different types of missions. All right, so how does Rafale play in all of this? Well, Rafale has vast experience when it comes to space propulsion. Rafale has been in the space propulsion market for over 3 decades now. Rafale systems are on board more than 66 satellites. Some are quite famous, such as Galileo, Sentinel, ExoMars, and Venus. These systems, these components are anywhere between basic components such as valves or thrusters or propellant tanks, and up to entire modules, propulsion systems that are just mounted on board a satellite and operate. These capabilities span from chemical thrusters, usually based on hydrazine, through cold gas propulsion systems, nitrogen or krypton, which we'll talk about in a second, and electric propulsion. A very good example for electric propulsion system, actually a dual propulsion system that contains both chemical and electric propulsion, is Venus. Venus is in space, it's successful, you already heard that a couple of hours ago. Venus includes an electric propulsion system and a chemical propulsion system. Both are successful now. And what we want to do at Rafale, we wanted to leverage on the know-how and experience that we gained over the past 3 decades and come up with solutions, proper solutions for these small satellites. We wanted to come up with the ideal propulsion system. So, I'll present 3 systems: cold gas, chemical, and electric propulsion system. Each one is suitable for different type of missions, different type of customers, different capabilities. The first one is a cold gas propulsion system. It's a compact 2-use system, weighs merely 2.1 kilograms, and delivers a moderate 160 Newton seconds of total impulse. To translate that into delta V capabilities, for an average 6U satellite, the system delivers about 20 meters per second delta V. This system, actually 3 of these systems, will be launched and will operate later on this year on board the Samsung nano satellites delivered by the Technion. Very interesting. So, if the required mission or mission requirements are for a light system, very simple, not too high delta V, the system is suitable. Moving on to the monoprop system, based on either hydrazine or can also use the hydrogen peroxide. It's a larger system, 5U, suitable for larger spacecraft, probably 12U and above. Roughly light system, 5 kilograms, and delivers a very high, very impressive 4 kilonewton seconds. So this system that generates quite high thrust, about 2 newtons if 2 thrusters are operational, can be used for quick-to-respond missions. Missions in which the satellite is large enough, you need to avoid space debris, for example, or you need to perform quick maneuvers, and so on. Third system, the electric propulsion system, still under development, is also a small 2U system. Weighs 7 kilograms, requires 100 watts, but since it is an electric propulsion system, it delivers very high total impulse, 10 kilonewton seconds. So this little guy here, once you plug it into a small satellite, you can do everything with the satellite. So this is suitable mainly for flocks of satellites that are either launched to, let's say, 300 kilometers altitude. And these satellites need to confront drag, for example. Or you launch them to 300 kilometers altitude and they need to go up to about 600 or 700 or 800 kilometers. They can do that. Then they can deorbit. All right? So what I'm trying to convey here is that there isn't one perfect solution here, and everything is possible. So the right question is not whether we need a propulsion system, is which one of these we need. All right? So depends on the customer needs. The system can be tailored. Okay, it can be changed, and if you're interested, you're more than welcome to stop by our booth. Of course, here outside you can see 2 of the models here, and of course, talk to us. So, thank you very much.